start with objective 29 today. We are going to find the inverse of the function, and we are going to determine whether two functions are inverses of each other. When you think of the word inverse, what do you think of? Opposite. Very good. So, for example, the inverse to a quadratic equation, the opposite of squaring, would be a square root, a radical equation, okay? They are inverses of each other. If we have points, let's just say the point 2 comma 3 is on one function. What point would be on the other function if it's the opposite? If it's 2 comma 3, then on the opposite it would be 3 comma 2. Very good. So I think you already have a handle on what we're going to be doing. So what happens to our x's and our y's with the inverse? They just switch, okay? And so here's your definition. I'll let you be working on. What I'm going to let you do in second block today, I talked about it as they wrote it, and then after I said, do you have any questions? They said, to be honest with you, I was just writing it down, and I didn't hear what you said. So I'm going to let you write it down first, and then we're going to discuss it. So let's talk about this for just a minute. Okay, first of all, the inverse function is denoted, if your regular function, if your first function is denoted with f at x, then the inverse is f to the negative 1 of x. When you see f to the negative 1 of x, that is implying the inverse of the function f at x. Okay, f at x and its inverse. Okay, the inverse of the function can be found by exchanging the domain and the range. Well, you just told me that. What's the domain? The domain is your x and the range is your y. So we're going to exchange them, and that's how we're going to find the inverse of the function. Also, if two functions are inverses of each other, both of their compositions, we're going to do the composition test. When we find f at g at x, everything will cancel out and you will be left with x. And if you're left with x, then they are inverses of each other. If things don't cancel out, and it should make sense, like, for example, the inverse of a cubic function would be the cube root. What happens when you plug a cube root into a cube? What happens to the cube and the cube root? They cancel. Things seem to cancel. When you are taking opposites and plugging them into each other, things are going to cancel. And at the end of the day, you should, if they are inverses of each other, you will be left with x. Okay? I have seen on like practice SOLs and things like that, they will say like, two functions are inverses of each other if, and they'll have f at g at x and g at f at x equals 0. F at x and g at f at x is equal to 1. F at g at x and g at f at x is equal to x. So which one would be correct? If they are inverses of each other, it should be equal at the end of the day. Once you do the composition and once you plug in, what should you be left with? So at the end of the day, once you find the composition, everything should cancel and you should be left with x if they are inverses. And if you're left with other stuff besides that, then they're not inverses of each other. Okay, does that make sense to you? Yes, question. Your answer would just be x, right? Well, 1x. 1x is x, but yeah, not negative x, not 3x, not x plus 9, just x. And if it's just x, after when you do f at g at x or g at f at x, it doesn't matter. Okay, it should just be x. And if it's not that, then they're not inverses of each other. Well, I mean, x is always a variable and could equal something, but you'll see when we do it, we're going to do a test, and we're going to find f at g at x. And when you take one function and plug it into the other, if they're inverses of each other, things should cancel out, and you should be just left with x. If they're inverses. That's what the test says. Okay? Good question, though. Very good question. All right. Example 1. We are going to find the inverse of each function, and then we're going to graph the function and its inverse. And I'm going to give you some graph paper. Let me know if you need some more. I've got a couple extra pieces. All right, so first things first is we have our function. Okay, this is our f at x function. In order to find its inverses, what does the definition say? In order to find an inverse, we need to take the x and the y and do what with them? Switch them. So I'm going to put the x where the y is, and I'm going to put the y where the x is. From there, generally, it's not just a matter of switching them. How do we normally like for equations to be written? In y equals. So you need to switch them and solve it for y, and that will give you the inverse, okay? So we're going to solve this guy for y, so we're going to move the 5 over, and this will be x plus 5 equals 2y. And then we are going to divide by 2 here, here, and here, so this will be 1/2 x plus 5 halves is equal to y. And so I'll make this in blue. This f to the negative 1 of x. This is our inverse function. Okay, so y equals 2x minus 5 and y equals 1/2 x plus 5 halves are inverses of each other. They are opposites of each other. Okay, and so what we're going to do is we're going to graph them. We're going to graph the original function and we're going to graph the inverse of it. Okay, so I'm going to graph the original one in black. You could, this would be a nice and easy one to graph in mx plus b form. Where's the starting point? At negative 5, so we're going to go down 5. And then from there, the slope has up to and over 1. Up to and over 1, because I'm doing the top equation first. Up to and over 1. Up to and over 1. Up to and over 1. What if it's not that easy? What if, like on the next one, the starting point is a fraction? So it's not that easy. How else might we graph? I mean, if it's in basic mx plus b form, then I would say yes. Just graph it using your slope and your y-intercept. But if it's not in that form, or how many will admit that you don't really remember mx plus b form and struggle with that? Okay, some of us might not remember that. So how else might we graph? Calculator. Okay, so what you're going to do is you're going to get your calculator. And what are we going to do once we put this in the calculator? So let's put in the bottom one. Let's put in the inverse, and I'm going to graph it in blue. So put in 1/2 x plus 5 halves. And I want you, make sure you put parentheses around the fractions. I want you to go to your table, and I want you to find me some clear points. So put in 1/2 x plus 5 halves. What's a good clear point to plot? I see 3, 4. Over 3 and up 4. Okay. What's another good clear point? 1, 3. And check this out. Over 1 and up 3. Check this out. On our first function, the point was, one of the clear points was 3, 1. Does it make sense that on our inverse function, one of the clear points is 1, 3? Does that make sense? Why? Because they're just opposite from each other. They're just switched, okay? So, and from there you can keep going with clear points, or I can see that the slope is up 1 and over 2, so I can go down 1 and left 2, down and left, and I can get some more clear points on there. Again, you can use your table if you would like to have clear points. And so I'm going to denote, my blue line is my inverse function, f to the negative 1 of x. And my black line is my original. That is my f at x function. Now, something else that I want to show you is that if you graph the line, inverse functions, remember how I told you last week when we were doing parent functions, when you had like parabolas. And we know the inverse to a quadratic equation is a square root. What happens to the parabola when it's a square root, the inverse of it? Do y'all remember? If it doesn't flip down, it flips it on its side. It makes like a C instead of a U, okay? So more than that, I'm going to expand on that a little bit. It actually inverses reflect across the line of y equals x. The line y equals x, they reflect across this line. So I'm going to make this in red. That would be 1x plus 0. So if crossing at the origin and up 1 over 1, if I drew this diagonal line, this is the line that they're going to reflect across or flip over. So what I mean is, if you, and I want you to actually take your paper, if you draw that line, that red line, does everybody understand which red line I drew? It's just the line y equals x. Okay? And you fold your paper on that line. What should happen to the blue and the black function? They should lay on top of each other. Does that make sense? They should, so if you fold it, and I want you to try it because I think it's very important that you try it. Take your paper and I want you to fold it on the line y equals x, on that red diagonal line. That's the line you're going to fold it on. And I want you to see, does your two functions, do they fold on top of each other? They should. Do they? You might want to fold it backwards. Does that make sense? So you can see that this line right here is where this line is. Or, I mean, you can fold it this way too, and you can see that this line is going to fold right on top of that line. Does that make sense? So that is your line of reflection. That is your line of reflection. So we're actually going to be drawing 3 lines on each, and I encourage you to fold it and try it. The more times, if I just tell you that that is your line of reflection and that the inverse will reflect across to the original function and they should be on top of each other, if you're actually folding it and seeing it, you'll remember it. Okay, so let me just recap here. The black line is my original function. That's y equals 2x minus 5. The blue line is my inverse function. It's what we found when we switched the x and the y and solved for y. And the red line is the line of reflection, the line that the black and the blue are reflecting across. Do you understand that? Huh? It does that every time. Inverses will reflect across that diagonal line. Okay? And so we'll look at that as we continue on with this. Okay, we'll look at that as we continue on this. Let me know if you have questions. Let me know if I've lost you anywhere. So the first thing that we are going to do is we are going to find the inverse. What do I have to do to find the inverse of that function? We need to switch the x and the y. And not just switch the x and the y, what else? Solve for y. We're going to switch the x and the y and then solve it for y. So I'm going to move the 1 over here, and this will be x minus 1 equals y squared, and then what? take the square root on both sides, and so y is equal to the square root of x minus 1. Now, if I just graph the positive square root of x minus 1, what's going to happen? It's only going to give me the top half of my parabola on its side, right? Okay, so if I want the bottom half, we want to make sure to do the negative square root. So this is now our inverse function. That's your f to the negative 1 of x. So I'm going to graph the original one, my f at x, in purple. So you can go to your calculators and you can put in y equals x squared plus 1. And we can go to our table. What's a good clear point to plot? 1, 2? Over 1, up. I'm doing the top one first. I'm doing the original. So over 1 and up 2. And what else? 0, 1. What else? What are over 2 and up 5? What about some negatives? Because that's only going to give me negative 1 up 2, because that'll give us our parabola. 2 up 5, and is it 3, 10? Which I don't think, I know you can't do 10 on yours, but I can do 10 on mine. Oh, can you? Good. I didn't know if you had enough room or not. Okay, and that makes sense. Does it make sense, just reviewing what we did last week, does it make sense that our parent function has shifted up 1? Because that's where I'm at. Does this make sense that I've shifted up 1? Why? Because I'm adding 1. Yeah, on the end. Don't forget that. Remember, if you add or subtract to the end of the function, it's going to shift it up or down. If you are adding 1 or subtracting 1 on the inside, it's going to shift it left or right. And if it like subtracting 1, where would it shift it on the inside? To the right. We do opposite from what we think, right? To the right. So don't forget about that. So that makes sense to us. Okay? So let's put in this function. Y equals the square root of x minus 1. Well, and it will be errors because there's not going to be anywhere on the negative side. Yeah. So I'm going to graph this one in red. So where's some good points? And that makes sense to us. Check this out. If on my regular function the point is 0, 1, does it make sense that on my inverse it's 1, 0? Like I could graph this without my calculator right now. If my regular function was over 1 and up 2, then what would I want on my inverse? Over 2 and up 1. Do you understand that? If on the regular function it was 2, 5, then on my inverse function, what am I going to want to plot? 5 up 2. And if it's over 3 and up 10, then on the inverse, I would want over 10 and up 3. Now, that only gives us part of the radical function. If I want the other half of it, then what do I need to do? I need to put the negative square root of x minus 1. That's not good. And so I would have, and again, you can use it if you know your original function. If the original function is negative 1 up 2, then you know on the inverse it's going to be 2, negative 1. Yeah, you're still going to get some errors on the negatives because it's not going to, not on your table. Well, find the clear ones. You should have 1, 0. Not on the negatives, you don't. I mean, in the positives. You have errors when x is negative. Look, check this out. Look at x is negative right here. Does your inverse go over in there? The inverse does not travel over into the negative on the x's. So you got to be on the positive side. And so it's going to look something like so. Okay? Now, I need to draw my third line. This is my function, f at x. Down here is my inverse function. What other line do I need? The line of reflection. So it will always, and I think it's good, again, the line of reflection is the y equals x line. That means 1x plus 0. Means it crosses through the origin. Okay, it's the parent function of the linear, right? It's the y equals x, the parent function of the linear. If you folded this on the blue line, if you folded it on the blue line, the purple graph and the red graph should match up. Does that make sense? It should match up if you fold it. And I encourage you, take your piece of paper and fold it. Try it. Okay? Physically put your, and make sure that it matches up. That way you will remember it. Okay? If you're just staring at your paper, it's not going to sink in. Okay, so I would like for you to try this one on your own. See how far you can get with it. So step number 1, in order to find the inverse, we need to take the x and the y and do what with them? Switch them. And then we're going to solve for y. So I'm going to take everything and times it by 5. And I get 5x. The 5's cancel here, and I get y minus 3. And then I'm going to move over here and get 5x plus 3 equals y. And that is your inverse. So how many were able to get to the inverse? Y equals 5x plus 3. Yes? Good. Any questions on how to get to the inverse? From there, I'm going to graph the top one in purple. So I'm going to graph my original function in purple. And I would put that in your calculator. What are some clear points for this one? 0, 3? Or is it 3, 0? Is it 0, 3 or 3, 0? For the top one, should be 3, 0. Yeah. Okay, so I'm going to graph the original one first. So 0, 3 is a good point. Or excuse me, 3, 0. 3, 0 is a good point. How about -2? -1 is a good point. -7, -2 is a good point. So it should look something like this. Okay, and so there's your original. I'm going to graph the inverse in blue. And that one, to me, that was a very nice mx plus b. So I'm just going to use my y-intercept. I'm going to go up 3. From there, I'm going to travel up 5 and over 1. Or I can travel down 5 and left 1. Whoops, and left 1. So it should look something like this. And so there's your inverse function. Okay. If you graphed your line of reflection, hang on just a second, should look something like that, and the blue line should match up with the purple line. Okay, we'll finish this when you get back from lunch. Okay, so I'm going to start with my first function. This will be my f at x. And to find my inverse, we are going to just take the x and the y and switch them. And it's not just a matter of switching them. Once I switch them, and then I must solve for y. So I'm going to divide both sides by 3, and y squared is equal to x over 3. And then once the y is by itself, then I'm going to take the square root on both sides. So this will be y equals plus or minus the square root of x over 3. How many were able to get there? Any questions? Did I lose anybody? Now would be a great time to ask. Okay, so then I'm going to graph my original function in blue. And let's take a look at this. Let's just talk and refer back to what we were doing the other day with our parent function. What happens, we know when we add or subtract on the end of it, it's going to move it up or down, right? And we know that if I add or subtract on the inside, like if I had the quantity of x plus 3 on the inside squared, then that would shift it to the left because it says plus 3, so it's going to shift it to the left. But what if you're multiplying by a number? What if you're multiplying by a number greater than 1? What happens? Our normal parabola looks like this. Everybody look, eyes up here. Our normal parabola looks like this. So if I times it by 3, what's going to happen to it? Does that make sense? Remember my rubber band that I had? It's going to vertically stretch it, and so it's going to make it skinnier. Okay? If I multiply it by something less than 1, say like 1/2 or 1/3, or 1/4, it's going to take your parabola and make it wider. Does everybody understand that? So just refreshing our memory. So we should see here when I graph this, it should be a skinnier parabola. So I think a clear point is at 0, 0. What's another clear point? For the 1, 3, so over 1 and up 3. And then the other one would be over 1, negative 1 and up 3. And so it's going to look something like this. And is that skinnier than the normal parent function? Yes, it is. And so then if I graph the inverse function in purple, I can do this without a calculator. You just take all the points you have and just flip the x and the y. So I'm going to start at 0, 0. If my parent function or the first function is 1, 3, then I know on the inverse it's going to be 3, 1. And then I can do the 3, negative 1. So it should look something like this. Okay? If you put it in your calculator, remember to get the top half of it, you put in the positive. And then to get the negative, we'll give you the bottom half of the function. Okay? And don't forget about your line of reflection. The line of reflection is y equals x. And if you folded right along on the red line, the blue and the purple should lay on top of each other. Those that were saying you were confused or lost, can I assist you anywhere, shape, or form? Are you okay? All right, are you okay with graphing them and finding the inverse? Because I'm going to go on to part 2, if that's all right. All right, part 2 says this. We are going to determine whether each pair of functions are inverses of each other, which means we're going to do the composition test. And what did I tell you in the beginning of the block today? If they are inverses, f at g at x should equal what? X. Okay, so we're going to try it. We're just going to do our composition test and see if these are inverses of each other. So I'm going to start with f at g at x. So we're going to start with g at x, which is 1/3 x minus 3. And we're going to plug it into 3x plus 9. So when I take this and put it in right here, you will get 3 times quantity of 1/3 x minus 3 plus 9. So far, so good? Just doing what we've done the past 2 days. And then When I times by 3, what happens when I times 1/3 by 3? The 3's cancel and you're left with x, and 3 times -3 is -9. And what happens to -9 and +9? They cancel, so our composition is equal to x. Does that work? Does that mean they are inverses of each other? Yes, it does. So this is going to be a yes. And if you reverse it, if I were to reverse it and do g at f at x, it should work as well. Okay, if one of them works, one of the compositions work, the other one should work as well. And sometimes, like, it might be easier to do one than the other. Do you understand what I'm saying? Sometimes it's easier to plug in a certain function instead of doing the opposite. So what if you get into plugging in one and you get lost? Just do the other way. Okay, plug in the other one. So just to show you, if I start with 3x plus 9 and plug it into 1/3 x minus 3, so this would be equal to 1/3 times 3x plus 9 minus 3. So 1/3 times 3 cancels and you're left with x. 1/3 of 9 is just 3, and my 3's cancel, and so I'm left with x. So these work. Okay, these two functions, f at x and g at x, are inverses of each other because when we do the composition test, it's equal to x. Yes, this is as hard as it's going to get, I think. 8. So we have three more. Okay, so you try this one. I want you to do the composition test. I want you to find f at g at x or g at f at x and see if they are inverses of each other. Okay, so are these inverses of each other? No. Okay, if we try, whoops, let's go back. If we try f at g at x, and so I'm going to start with g at x, which is 2 times the square root of x, and we plug it into 4x squared. So this will be 4 times 2 times the square root of x squared. I think the easiest thing for you to do is take this and write it twice. You don't have to. This one, you could actually take the 2 to the 2 and the 2 to the square x because it's a monomial on the inside. But keeping in the same trend that we've been working with, how do you multiply 3 things together at once? Take 2 of them, times them together. So let's take these 2 and times them together. 2 times 2, outside with outside. 4, inside with inside. What's square root of x times square root of x? Just x. Technically, it's the square root of x squared, but the square root of x squared is just x. Okay? And don't forget you have this 4, so then you get 16x. So does that pass the composition test? No. Okay? Goodness gracious, no. Okay? It does not pass composition test. So they would not be inverses of each other. And so, again, someone said, did anybody take it and say, I don't want to plug the square root into the square? Did anybody take it and say, I would rather plug 4x in there? And that would be just fine if you plugged in 4x squared there. What is the square root of 4x squared? 2x, and so you get 4x this way. Either way, it still fails the composition test. So these are not inverses of each other. This would be a no. Okay, so 2 more. Try this one. Are these inverses of each other? No. Do you need to see it? Just one of them or both of them? F at g at x. Okay. Whoops. All right. So if I find f at g at x, I'm going to start with g at x, and that is 1/3 x plus 4. And I'm going to plug it into 3x minus 3. So I'm going to take this and put it in there. Be quiet, please. Plus 4 minus 3. So what happens? 3 times a third is 1x, or just x. 3 times 4 is 12. And then 12 minus 3 is x plus 9. And even though the x is by itself, you still have the plus 9. So that fails the composition test. So that would be a no. So we'll write no. All right, last one. Last one. Try this one. Are they inverses of each other? And I am going to work it out just because of the radical. So if I find f at g at x, I even like these compositions better than like what we were doing yesterday and the day before, because what should happen? And when things start to cancel, it's pretty easy, right? So if I start at f at g at x, if I start with g at x, so the square root of x plus 1 over 2, and I'm going to plug that in right here. So the square root of x plus 1 over 2 squared minus 1. So not only do I get to sing my jam, what's my jam? What happens to the square and the square root? Can't, because it was right here. Because it was right here. So this is 2x squared minus 1. So I brought the 2 stays in it. The only thing I did is I replaced this x with the g at x function. No. The only thing that goes inside the parentheses is what you're plugging in. I'm plugging this in for the x. So let me go back. So it's the same thing you did yesterday on your quiz. So we're plugging, for f at g at x, we're plugging into the f at x function, which is 2x squared minus 1. So this is the g at x function, and I'm going to plug it right in for this x. So I'm going to bring down the 2. In place of the x, I'm going to put in the square root of x plus 1 over 2. And I'm going to put the square on the outside and then the minus 1. Okay? So then the square and the square root cancel. And you're left with x plus 1 over 2. What should happen to the 2's? Cancel. And you're left with x plus 1 minus 1. And what happens to the 1's? Cancel. And you're left with just x, which does satisfy the composition. Yep. To my knowledge, if one of them works, the other should as well. Okay, I don't know. I can't think of a time when one would work and the other wouldn't. No, you do not have to do the other one. It does not hurt, because what if you do one, but you make a careless error? You see what I'm saying? So it may benefit you to try the other one. And so just in case we do the other one, it should work as well. If one works, the other should work. So I'm going to take g, or f at x, which is 2x squared minus 1, and I'm going to plug it into the square root of x plus 1 over 2. So watch this. So when you plug this in here, I'm going to plug it in right for this x. 2x squared minus 1. Then I'm going to write the plus 1 over 2. So what happens minus 1 plus 1? Cancel. And so then I get the square root of 2x squared over 2. What happens to the 2's? Cancel. And then what's the square root of x squared? Just x. So it should work. Either way, it should work. Okay? All right. And my favorite slide of the day? Quality mean? So I'll have to tell you a story. I'll have to tell you a story about these.